Okay, good morning everyone, or rather good afternoon. My name is Preshanthan Moodley and I'm from the University of KwaZulu-Natal in South Africa. And today I'm going to be presenting to you a portion of my master's research, which deals with dilute acid pretreatment techniques for fermentable sugar production from sugarcane leaves. As we are all aware, current fossil fuel reserves are rapidly depleting. And some studies have estimated that within the next 150 years, fossil fuel oil, coal, and gas could be completely diminished. To add to that, the usage of these fossil fuels is contributing to the phenomenon that we all know as global warming. So this is why scientists such as ourselves are on a quest to find a new source of energy. Now, to put this into perspective, if you were to ask somebody, let's say in the 80s, what the future would look like, they would have described a utopian-like world. Clear skies, green grass, flying cars. However, if you have to ask someone that question today, they would probably describe a very polluted, very uninhabitable world, or, as some scientists say, a world completely underwater. This is why we need to find a new source of energy. The source for this energy should be something that is sustainable, something that is abundant, and preferably something that is waste. This is why lignocellulosic biomass is showing a lot of promise as being a potential feedstock for biofuel production. Annually, approximately 200 billion tons of this material is produced, and most of this material is actually considered waste. Now, this type of material is composed of cellulose, hemicellulose, and lignin, and those components in themselves are very rich in fermentable sugars. However, pretreatment of this material is necessary in order to make these sugars accessible to the microorganisms. If we look at sugarcane, annually approximately 1.6 billion tons of sugarcane is produced annually. And that clearly indicates to us that sugarcane is an important agricultural crop globally. The leaf component, which comprises approximately 40% of the plant, is considered waste. And judging from that figure, you can only imagine how much of waste is actually generated. Now, unfortunately, this waste is disposed of either by dumping in landfill sites, or more commonly, by burning. Now, aside from the massive CO2 emissions that result from this burning process, several studies have found that benzofluoranthene and benzopyrene, which are mutagenic particles, are released in this burning process. So this is why we suggest, instead of burning these leaves, they be channeled towards bioprocess applications. Looking back at pretreatment, this is a process, as I've mentioned, that is often necessary because it allows the dissolution of the cellulose matrix. For this study, an acid-based hybrid technique was used. This comprised of milling, thermal, and acid treatment. 3 acids were assessed: hydrochloric acid, sulfuric acid, and nitric acid. For the experimental design, the response surface methodology was used, more specifically the Box-Benken design. 4 parameters were tested: acid concentration, temperature, heating time, and solid to liquid ratio, and the ranges are shown here in brackets. 29 runs was generated from the software, and each of these runs was carried out in the laboratory. For the pretreatment process, the leaves were dried at 60 degrees for 72 hours and was then milled using an industrial miller to reduce the particle size to approximately 1 millimeter. Varied amounts of the dried powder was then added to 20 moles of acid of varied concentrations as set out in the design. The heating was then initiated only once the set point temperature had been reached in the flask of the mixture. The sugar that was released from each of these runs was quantified using the YSI 2700 sugar analyzer. Once the sugar had been recorded, it was then added to the 2 columns for the responses and then fed back into the software. And the software then performed an analysis of variance or ANOVA. And it then created models for xylose and glucose for each of the acids that were assessed. These are the polynomial equations that were generated for the hydrochloric acid pretreatment. And I just want to make a note that these equations relate the glucose and xylose yield patterns relating rather to the input parameters that were assessed. For a statistical model to be significant, R-squared values, or coefficients of determination, between 0.7 and 1 should be obtained. Now, as you can see here, both R-squared values were above 0.7, indicating model significance. If we look at the model equations, we can see that term A for both xylose and glucose has the greatest effect on the yield of sugar. And here, term A relates to acid concentration. A similar effect is seen with the sulfuric acid pretreatment. First of all, the R-squared values, again, above 0.7, indicating model significance. And term A, again, contributes the most significantly towards sugar yield. And again, that relates to temperature. Something slightly different is observed for nitric acid. With glucose, it's very similar to the others, where term A has the greatest effect, and that is acid concentration. However, when we're looking at xylose, term C actually has the greatest effect on the yield of sugar. And here, term C relates to temperature. Looking at the response surface graphs, these graphs show us the interactive effect of the various input parameters on the yield of sugar. Now, we can see here that if temperature and acid concentration is increased simultaneously, the sugar content increases quite significantly for both xylose and glucose. Similar effects, again, is seen with sulfuric acid, where an increase in temperature and acid concentration increases your sugar quite significantly. Looking at nitric acid, if we look at xylose, now, as I've mentioned before with the polynomial equations, you will see what I mean here. If we had to keep acid concentration constant at any of these set points and increase temperature, you can see there is a huge difference in the yield of sugar. However, if we had to keep the temperature constant at any of these points and increase acid concentration, the yield of sugar isn't as significant. So this obviously ties in with the polynomial model, which indicated that temperature has the greatest effect on the yield of sugar. The next step was optimization, where the model predicted which set points would be optimal to release maximum sugar. And the conditions are all shown here. And since these conditions fell within the search range, that again indicated that the search range was well chosen. The predicted values are shown here in this column. And these conditions were carried out in the laboratory in replicates in order to see if the results we get are very similar to the predicted values. We can see that with HCl, the values were very similar compared to the predicted values. And as we move down the tables to sulfuric acid and then nitric acid, the values vary quite similarly. Scanning electron microscopy was then carried out in order to visualize any structural changes on the surface of the sugarcane leaf. By looking at the native leaf, we can see a smooth, intact epidermal surface. However, after pretreatment, we can see major structural changes or damage on the epidermal layer of the sugarcane leaf. The next analysis we did was detergent fiber analysis in order to determine the solubilization of the various layers. And as we can see here, that with hydrochloric acid, we had a 93% solubilization, with sulfuric acid, a 92% solubilization, and with nitric acid, a 79% solubilization. The next stage was an assessment for biohydrogen production. Now for this, we adopted a 1.5 liter working volume. 600 moles of the pre-treated substrate was added to give a final sugar concentration of approximately 12 grams per liter. 600 moles of a supplementary mineral salt mix was added, followed by 300 moles of anaerobic sludge. Now the sludge was heat treated at 121 degrees for 10 minutes in order to deactivate any hydrogen consumers in the sludge. The flask was then flushed with nitrogen gas for approximately 5 minutes, and the process was run at a pH of 6.5 at 37 degrees Celsius at 180 RPM for approximately 72 hours. A peak hydrogen fraction of just over 40% was obtained, together with a cumulative volume of just under 200 moles and a hydrogen yield of 18.6 moles per gram of fermentable sugar. To conclude my presentation today, 3 models were successfully developed which related the yield of xylose and glucose generation from waste sugarcane leaves using hydrochloric acid, sulfuric acid, and nitric acid. Results indicated that hydrochloric acid was the most effective acid and gave a yield of approximately 78 and 11.48 grams per liter of xylose and glucose, respectively. A hydrogen assessment gave 191 moles, and putting all of this into perspective, we can see that sugarcane leaves is in fact a promising feedstock for the production of biofuels. And perhaps the most significant finding of this work is that by using sugarcane leaves in this context, we can alleviate the burden that the burning puts on the environment, and at the same time, we are adding value to waste. Thank you.